Okay, now next property, interference, which we've talked about a number of times. We talked about it generically, we talked about it in the sound unit. So we really don't have to hit on interference patterns too much, other than to say you can have constructive interference when a peak meets a peak and a trough meets a trough. You get reinforcement, so what property is enhanced? The amplitude is enhanced. When a peak meets a trough and a trough meets a peak, then you get cancellation. And then you can get any flavor of partial cancellation in between the maximum reinforcement and total cancellation. Okay, now when we look at that with light, imagine that these are two identical light waves that are near each other and that have interaction with each other. You can see that there's constructive and destructive interference patterns. Okay, depending on how far apart they are relative to the wavelength, you might get more or less interference. Okay, now also, this could be light being shown through two neighboring slits, two neighboring barriers, where they're diffracting, and then the resulting diffraction causes interference patterns. This can be seen with monochromatic light, like a laser beam shown through a double slit. There's diffraction here, and then the diffraction patterns interfere with each other, and the resulting interference, you get constructive interference where you have bright light, and then dark would be the destructive interference, constructive, destructive, constructive, destructive. Okay, so we're getting twin properties here, diffraction through the slits, and then the resulting interference pattern. So this is an actual physical representation of this ripple tank scenario. Okay, now here's what you would actually see with a laser being shown through a double slit. This is an actual photograph of the experiment. Now, interference patterns can be pretty complicated, and much of the rest of the notes will look at that complicated. This was an interference pattern of a, gosh, what's the name of this object? Mirage mirror or something. You place an object. This is two concave mirrors, one here and one here, with an opening at the top. And then you put an object down here, in this case, a small model of a frog. And then the reflection of the frog bounces off of this mirror down and then back up, and you're getting all kinds of interference between the rays from all parts of the frog. The result is a perfect three-dimensional virtual image of a frog, what looks an awful lot like a hologram of the frog. This is a more complicated one. It looks like a cup of coffee beans spilled over, that's sitting on top of a mirror. And it is, but the coffee and the coffee cup and beans are down inside this double concave system. So it looks like it's sitting on top here with the mirrored surface and the cup sitting right on the mirrored surface, but it's actually down here. Okay, another case of diffraction and interference together is a diffraction grating, which is a thin film with thousands of lines per square inch. So we're getting massive numbers of diffraction patterns and interference patterns. And when you shine light through it, you get a dispersion of the entire spectrum of the visible light. If you remember back in chemistry when we looked at the flame test lab or the neon light box, and you had diffraction gratings that you held up to your eye, and you looked at the neon light through the diffraction grating, you saw a series of bright lines. And that's with an element's individual spectrum. With white light, you get the whole rainbow of light. So you can get dispersion like through a prism with refraction. You can also get dispersion with a diffraction grating like this. You can also get dispersion with a CD, with a peacock feather or hummingbird throat feathers. And all three, or these two, actually all three of these are called iridescence. So you get the reflecting of light off of different kind of depths of surfaces, um, and then the resulting interference pattern as they reflect at different angles gives you this broad spectrum. And then a similar thing with soap bubbles. Soap bubbles and oil slicks, or this is a gasoline stain on a driveway. Okay, so you have air and gasoline and water, and the gasoline is in different depths. In fact, you can think of this as kind of a topo map where the gasoline is at different depths. So you have light that's reflecting off the surface of the gasoline, and as well as the surface of the water. And because of the refraction of the gasoline as it travels through and at different depths, you're going to get different interference patterns. Some cancel out all but the blue light, some cancel out all but the violet light, some cancel out all but the yellow light, and so on. So you end up with a dispersion of light called iridescence, much like this.